Hi, hello everyone. Welcome back to my YouTube channel, Sporify Learn. Today, let's discuss about the second PUC first chapter in chemistry, that is solutions. Let's see on through it. I'm trying to cover all the NCRT parts which is present in that textbook, and let's see from line by line. In normal life, we rarely come across pure substances. Some of these are mixtures containing of two or more pure substances. Okay, mixtures are nothing but containing two or more pure substances. Their utility or importance in life depends on their composition. For example, if you take brass, it is mixture of copper and zinc, and German silver is mixture of copper, zinc and nickel, and bronze is of copper and tin. 1 parts per million, that is, of fluoride ions in water prevents tooth decay, that is helps in tooth decaying, and which 1.5 causes the tooth to become mottled, and high concentrations of fluoride ions can be poisonous also. And this is how we see, and in this unit we'll be discussing about their formation properties, and vapor pressure, colligative properties, and types of solutions, and various alternatives in which concentration will be acts as a solute. Now let's see the types of solutions first. There are mainly two types of solutions, that is homogeneous and heterogeneous, as we all know from before. Solutions are homogeneous mixtures of two or more components. See, they are the mixture of what? Two or more components. By homogeneous, we mean that their composition, remember the word composition, and properties are uniform throughout the mixture. Means they are same. Homo means what? Same. Homo meaning is what? Same. Generally, the component that is present in large quantity is known as solvent, and which is present in small quantity is known as solute. Okay, see, if we take any example for solvent and solute, if we take water solution, it is the solution, right? See, we say water solution, that is solution, in which water is the solvent, because that is present in more quantity, and salt is what? Present in less quantity, so it is solute. Okay, now we shall begin with binary solution, that is consisting of two components. Okay, now let's see what are the liquid, solid and gaseous states. Gaseous states means solute is gas, liquid, or solid, liquid or gas for liquid, and solid solutions. See, here the solvent will be present in more quantity, means for gaseous solutions gas will be only present in more quantity. Okay, this is in high quantity, this is in less quantity. Okay, now if we see for example mixture of oxygen and nitrogen gases. Okay, and for liquid and gas, like gas acts as solvent and liquid acts as solute. Here nitrogen is gas, that is present in more quantity, but mixture of oxygen is present in less quantity. Okay, now chloroform mixed with nitrogen gas, and camphor in nitrogen gas, that is for gas and solid. Okay, now if we come for the liquid solutions, gas, liquid and solid, here the liquid will be the solvent because it is present in more quantity, and this is present in less quantity, as they are solvent and solute. And oxygen dissolved in water is for gas and liquid, and because they are present, water is present in more quantity and gas is present in less quantity. And ethanol in water and glucose in water, glucose is present in solid form, right? If you dissolve that, it will be dissolved, in which water is present in more quantity. And for the solid, as solvent and gas, liquid, solid, here solution of hydrogen in palladium, amalgam of mercury with sodium, copper dissolved in gold. This is the table which you have to study, it's very important. Okay, it's very important table we have to study. Next, if we come to the expressing concentration of solutions, composition of a solution can be described by expressing its concentration. Okay, composition can be like it can be described or expressed in way of concentration, and the latter The letter can be expressed either quantitatively or qualitatively, in which quantitatively means we say that quantitatively means it says solution is dilute, or that is relatively very small quantity of solute, okay, or it is concentrated, that is rare very large quantity of solute, okay. For this you can take example of salt sugar solution or salt solution, like that. But in real life, these kinds of description can add to lot of confusions, and thus the need for a quantitative description of the solution. There are several ways by which we can describe the concentration quantitatively. Remember the word quantitatively, okay. Now let's see the mass percentage. This and all you have studied in first PUC. Now let's see on it deeper, okay. Mass percentage is represented by W divided by W, okay, percentage, right. Now it can be defined as mass of the component in the solution divided by total mass of the solution. Mass of the component, which component we have to find, that solution of mass divided by total mass into 100, because it is percentage, okay. For example, if you take 100 per 10% of glucose in water by mass, and 10 gram of glucose in 90 gram of water, in resulting in 100 gram of solution. Concentration percentage is commonly used in industrial applications, okay. And for example, commercial bleaching solution contains 3.62 mass percentage of sodium hypochlorite and water. If we come to the volume percentage, that is denoted by V by V, okay, this you can remember, volume V, okay. This also same, volume of that component divided by total volume into 100, because it is percentage. If you take 10% ethanol, and if you dissolve it in 10 ml of ethanol solution, and the total volume will be 100 ml, and this will be containing this. And if you see, it is solution, like 35% of volume percentage solution of ethylene glycol and an antifreeze is used in cars for cooling an engine, okay. Now if you see the next, volume, mass by volume, mass denoted by W, and volume is denoted by capital V, so that's why we write V divided by W divided by V. And another unit is which commonly used in medicine and pharmacy, and let's highlight this, medicine and pharmacy, and it is used in volume percentage. It is the mass of solute dissolved in 100 ml of solution. It is the mass, okay, mass of solute, okay, solute, okay, that is present in 100 ml of solution. Next, if we see parts per million, it is trace quantities, and that is expressed in number of parts of the component divided by now total number into 10 raised to 6, okay. As the percentage concentration in parts per million can be also expressed as mass to mass, volume to volume, and mass to volume, okay, as we see above. And if you take an example of a liter of sea water which weighs 1030 gram, contain 6 into 10 raised to minus 3 grams of dissolved oxygen, that is O2. Such a small concentration is also expressed as 5.8 gram per 10 raised to 6 gram of 5.8 ppm of seawater. The concentration of pollutants in water or atmosphere is often expressed as like, this is the unit of ppm, or we say for 1 ppm, see some value comma ppm we say, okay. This is how we express. This is mu gram milli per liter. Now if we see the mole fraction, it is fraction means what, it is having numerator as well as denominator, that is denoted by x, you think, and subscript, okay, that is denoted by x, denotes the component. If you say number of moles of the component divided by total number of moles, okay, this is not percentage, so we have not did into 100. And for particular in binary mixtures, we take moles of A and B are Na and Nb. If you take that, it will be Na divided by Na plus Nb, that is for particular mole fraction of particular A component. And for I, if you have n I divided by n1 plus n2 divided plus up to ni, and x, this is for very important, this is your mole fraction. Like if you add all the mole fractions unit, you will be having 1. To verify your answer, you can do this. It is one of the most important concept you have to understand is all the mole fraction, if you add, you will get it as unity. Unity is nothing but we say it as 1. Okay, I'll highlight if you want it. It is 1. Okay, now next is mole fraction unit is helpful. Now if we see the first example of this chapter, calculate the mole fraction. Okay, mole fraction of ethyl ethylene glycol, the formula they have given, in a solution containing 20% of ethylene glycol by mass. Okay, now let's see the molar mass. Molar mass, if we have to find out, we have to know all the individual molar masses, right? Carbon is 12, hydrogen is 1, and oxygen is 16. Carbon, that is having two elements, so 12 into 2, hydrogen is H6, so 1 into 6, that is hydrogen molar mass is 1 into 6, plus oxygen is 2. Okay, so 16 into 2, if you add all this, you will get as 62, and the SI unit of molar mass is gram per mole. Now if you say moles of this is molar mass. Okay, don't get confused, this is molar mass, and they have given moles. Okay, mole fraction we have to find, right? Now if you see, it is 20 gram. Okay, 20%. Okay, 20 gram divided by molar mass, we got it as 62 gram per mole. Here gram will get cancelled, and if you take mole here, it will become only more, because per mole will become, this will become plus 1. Okay, now if you say moles of water, okay, that is 80 gram, because see, in a solution means it will be of what, 100 percentage, right? In which 20% is ethylene glycol they have given. Okay, rest what is remaining in 100, it is 80, so we know that it is water. Okay, now if we take it is 18 gram per mole. If we calculate the H2O, right, 1 into 2 plus 16 you do, that is 2 plus 16, you get it as 18. Now you see that it is 18. Okay, now you can do this in calculator, 4.44 mole you will get. And for x is the symbol that we use to denote mole fraction. You can see it is 0.322 divided by 0.322, because they have asked ethylene glycol. Okay, ethylene glycol, and water also you can find out. If they have not mentioned anything, you have to find out both, and if you they have mentioned any particular, if you find that is enough, and you have to add and divide, and you will get the answer. If you add these both, you will get it as 1. Okay, if you want, you can check it. See, I'll only show 0.068, and here it is 0.932. Okay, here it is 10, obviously 1 carry 6 1 7 8 9 10 0 1 carry 9 plus 1 10 0 1 carry here 1 dot, that is unity. Okay, now if you have to find out the mole fraction of water, you can do as, see, 1 minus, see, as we know, if we add all the mole fraction, it will be 1, right? So if we, let me show, see, here we have mole fraction of glycol plus mole fraction of water is equal to 1, right? If we know this value as 0.068 plus, we don't know this value, so we write it as this. If we want this xw value, you can do 1 minus 0.068, right? So that is what they are saying here. And next concept is about molarity. If you take moles of solute divided by volume of solution, if we see this example, see, they have asked about 5 gram of NaOH in 450 ml of solution. See, 5 gram you take it here, and NaOH you find out formula, because they have said about NaOH, right, sodium. That is, if you find out the moles, it will be 40 gram per mole. You divide, you will get as 0.125. And volume of solution, like they have asked about molarity, right? So volumes of solution in liter you have to find. They have given in ml and divided by 1000 you do, and you will get the value. And if you do, it will be mole per liter also you can keep, or mole per dm cube. Okay. Molality, this is moles of solute divided by mass of solvent in kg. This is in solution in liter, where, yeah, it's solution in liter, this is solvent in kg. If you see this example, they have given CH3COOH, that is ethanoic acid, and you'll get moles as 0.01417 mole. And if you take for benzene, that is per kg, you will into 10 power minus 3 you will do, because they have given in gram and we want in kg, but here they had given in milliliter and we wanted in liter. Okay, now we'll get the answer as 0.556 mole per kg. Now let's discuss the next concept of this chapter, that is solubility. Solubility of a substance is its maximum amount that can be dissolved in a specific amount of solvent at a specified temperature. I hope you got this definition. That is nothing but how much the solvent will be dissolving in the particular solution. It is called as solubility, like at some specific temperature. This is one of the most important definition. It depends upon the nature of solute, solvent, as well as the temperature and well pressure. Okay. Let us consider the effect of those factors in solution. See, solubility of solid in liquid. Okay. They may be dissolving as solute plus solvent is solution, right? Or if you have the solution, it is solute plus solvent. How that works is every solid does not dissolve in given liquid. When sodium chloride and sugar dissolve readily, naphthalene and anthracene do not. Okay. On the other hand, naphthalene and anthracene dissolve in benzene, but not sodium and do not. Okay, so we are having some solutions that will dissolve in particular liquid or not, and in general, a solute dissolve in a solvent. A solute dissolves in a solvent if the intermolecular reactions are in the two or more, like we may say like dissolves like. Okay, next is effect of temperature. We will see about saturated solution. See, at this stage, we similar process. Okay, so if there is no more solute can be dissolved in the same temperature and pressure is called as saturated solutions, and unsaturated is nothing but the reverse of it and at the same temperature. And if we see the Le-Chatelier's principle, we already know that the solubility of a liquid and solid and liquid, or that is affected by its temperature. And consider the equilibrium represented by equation. Okay, now if we have delta of solution of H is greater than 0, that is for that will be for saturated solution, and this is exothermic for less than 0. And if you see the effect of pressure, it is pressure does not have significant effect of solubility of solids in liquid. It's so incompressible, it is incompressible. Now let's see about the gas in liquid. Most gases dissolved in water, but oxygen only to a small extent in water. In this dissolved, you can see all aquatic life, and hydrochloric gas is highly soluble in water. And if you see the temperature, the solubility of gas increase with that is directly proportional pressure, and the lower part is solution and the upper part is gaseous state in this given. Lower part is okay. Now Henry's law, we see the law states that the solubility of a gas in a liquid is directly proportional to the partial pressure of gas present in the partial pressure of the gas present above the surface of the liquid or solution. It is one of the most important and repeated question asked. And Dalton, a Dalton says that a contemporary of Henry also concluded, see, it is Dalton's law, okay, mole fraction of gas in the solution is proportional, okay, proportional means you can represent as the symbol, and partial pressure to the gas over the solution. The most commonly used form of Henry's law, this most commonly form is the partial pressure of gas is P, that we represented as P is directly proportional to mole fraction of the gas. See, partial pressure we represented by P. P is equal to KH. KH is the Henry's constant, and X is nothing but the mole fraction. This is the equation for Henry's law. Now if we see, these are the different values for temperature and Kelvin in and what are the values for Henry's constant also. You can go through that. Now here they have given the temperature and in 1 liter of water, and nitrogen is the element, and they have given the pressure with temperature and the K bar. You can substitute all the values and you can find out. Say they depend on the to like what are the uses of Henry's law is they are to increase the solubility of CO2, that is carbon dioxide, in soft drinks and soda water, and scuba divers. This is very important again. They'll ask, and at high altitudes and partial pressure is less, okay, so that will be at the ground level. This will in less low the concentration at oxygen, but the in the blood and tissues, people living at high altitudes or climbers, low that will be leading to the symptoms as anoxia, okay. Now if you see the effect of temperature, solubility of gases decreases, okay, they are inversely proportional, solubility of gases in liquid with temperature. Now if you see vapor pressure of liquid solution, they are liquid solutions are formed when solvent is a liquid, that is having more quantity, and if you see they are liquid in liquid and solid in liquid, that we will discuss in the table which they have given below. Now if you see the one of the most important law again after Henley's and Dalton, for a solution of volatile liquid, the partial vapor pressure, that is P, okay, we denoted it by P, of each component of the solution is directly proportional to its mole fraction, okay. See, they are saying here it is directly proportional to mole fraction, so if you remove the proportionality sign you will get equals, and you have to add one constant called as P1 naught, that is constant in Henry's law, but here we say that it is vapor pressure of pure component 1, okay. See, we say that it is component 1 because there is P1 naught, okay. And now for P2 naught also it is for some component 2 in the same way. And now we have discussed about the Dalton's law. See, according to Dalton's law, if you consider for partial pressure, the total over the phase in the container will be the sum of total pressure. Like if you take the P total, it will be the individual addition, okay, the pressures. And now the conditions if you take for they can be drawn in this form, and you can go through that. Now, Raoult's law as a special case of Henry's law. According to Raoult's law, the vapor pressure of a volatile component in a given solution is P1 is equal to Xi Py naught, and in the solution we denote it as P is equal to KHX, that is Henry's constant, partial vapor pressure and the mole fraction. Next, Raoult's law in its generation, like general form, we can say it as for any solution, the partial vapor pressure is directly proportional to its mole fraction. Now, another important is they'll ask the difference about this ideal and non-ideal. Ideal solutions are those, see, first let's discuss, they are the laws that obey Raoult's law, and the ideal, they have two different other properties, that is enthalpy of mixing of the pure components to form the solution is 0, and the volume of mixing is also 0. Delta mix of H is equal to 0 and delta volume is also 0. That means it is absorbed or evolved when the components are mixed. And now they will be having the interactions as intermolecular AB, BB and AB, and the forces between them is almost equal. Now if you see the non-ideal solutions, if you see they are the do not obey Raoult's law over the entire range of solution concentration. This is called as non-ideal solution. The positive derived deviation, and its law, it exhibits negative deviation also. See, we see for the negative and positive deviation, see they are having positive deviation is nothing but, you can see the graph, it is increasing and here it is decreasing. And now if you see, in case of negative deviations, you can see the intermolecular forces between A are weaker. Here it is stronger in positive deviations. And if you see azeotrope example, which are binary mixtures, they are having same composition in liquid and well as vapor phase and boil at constant temperature. In such cases, it is not possible to separate the components by fractional distillation. Now there are two types, minimum boiling azeotropes and maximum boiling azeotropes, and now let's discuss that. Now we have learned, okay, there are having relative lowering of vapor pressure of solvent, depression of freezing point, elevation of boiling point, and osmotic pressure. Okay, these are the four properties, colligative properties that we have. Now let's see about the relative lowering vapor pressure. That is, let's discuss this formula. P1, that is equal to x1 P1 naught, that is the reduction, if you see, that will be delta P1, and that will be P1 naught minus P1. Okay, P1 we can substitute this P1 divided by this. Okay, and if you take P1 not common, it will be 1 minus x1. The same way if you write the fraction, it is, and the expression on the left hand side of the equation as mentioned earlier is called relative lowering of vapor pressure and is equal to mole fraction of the solute. P1 naught minus P1 divided by P1 naught is equal to N2 divided by N1 plus N2, because X2, that is mole fraction of X2, is equal to N2 divided by N1 plus N2. Now let's discuss about the elevation of boiling point. If you take boiling point, that will be equal to delta TB is like directly proportional to M. Okay, that is the boiling point for elevation and boiling point. And KB here, if you remove this proportionality, you will get KB, that is the molar elevation constant or boiling point elevation constant. The unit of KB is Kelvin kg per mole. Values of KB for some common solvents are given in table 1.3. Now if you see this, M is equal to W2 divided by M2 divided by W1 divided by 1000, and it will be equal to 1000 into W2 divided by M2 into W1. Okay, because this if you take here and this, it will come down. Now if you see depression of freezing point, the graph you have to go through it. See, here we have on y-axis vapor pressure, on x-axis temperature, and we have the frozen solute solvent and liquid solvent and the solution, and here it is the freezing and the difference between them. Okay, now the this is delta TF is directly proportional to M. If you remove that, you will get a constant that is called as freezing point depression constant or molar depression constant or cryoscopic constant. Okay. Now if you see, the next concept is important, osmosis and osmotic pressure. Osmosis. Now if you see, there is solution. Okay, this is the solution, and here we have the solution, here we have the P, and here we have the H, that is, this is solvent and this is semi permeable membrane. Okay, now if you see the definition of osmosis, the See, membranes that are having properties, okay, SPM, we call semi-permeable membrane as SPM, and that will be having holes but passage of bigger molecules is allowed, like solute and hindered, like very in bigger molecules or bigger quantity, that is called as, through which it passes is called as membranes, that is semi-permeable membrane. And if this membrane is passed between solute and solution, that this through a pure solvent, like pure solvent will be of the solution, this process of flow is called as osmosis. And for osmotic pressure, the pressure that just stops this flow of solvent, okay, solvent is called as osmotic pressure of the solution. And the osmotic pressure of the solution is excess pressure that must be applied to a solution to prevent osmosis, okay. Now, pi is equal to, it is the osmotic pressure, and R is the gas constant, universal gas constant, C and RT, T is the temperature, and C is the solution. And now if we see, it is N2 divided by V RT, you replace C by this formula, and pi V is equal to W2 RT divided by M2, and M2 if you want you keep this, it will come here and this it will go here. And measurement of osmotic pressure is given by this. Two solutions having same osmotic pressure at given solution temperature is called as isotonic solutions, and which have different is called as hypertonic and hypotonic, if that is said to be like mass divided by volume, and this is 0.9% mass divided by volume sodium chloride. And such a solution, it would shrink, and this would be concentration is less than, and this is concentration is more than. Now if we see, um, puffiness or swelling is called as edema. Like what is that means? A raw mango placed in concentrated salt solution loses water via osmosis and shrivel into pickle, okay. Now that mass and water will move into cells through osmosis, and that raw mango is kept, right, that is having lost water, right, so that is through osmosis. And water when placed 0.9% less than is called as what, salt, and that is by osmosis again, and the resulting will lead in edema. Reverse osmosis is nothing but the direction of osmosis can be reversed, the direction can be reversed, okay. If a pressure is larger than osmotic pressure is applied to the solution side, that is now the pure solvent flow out of the solution through the semi permeable membrane, this phenomena is called as reverse osmosis, okay. Now see, here there is salt water and here it is fresh water, and this is the water droplets, and here it is the piston that is going out, pressure is greater than pi, okay. That is osmosis, and that is called as reverse osmosis. Now if we see abnormal molar masses, this is having boiling point 2 into 0.52 K is equal to 1.04 K, that is having the degree of dissociation. And this is the diagram, and if you see the formula, normal molar mass divided by abnormal, or you can say observed colligative property divided by calculated, total divided by number, and divided by dissociation, and that is having the colligative properties. If we see the last example, see this is having 0.6 milliliter of acetic acid, formula is CH3COH, and having the density of 1.06 gram milli per liter, and is dissolved in 1 liter of water. The depression in freezing point observed by for its strength of acid was 0.0205 degrees Celsius. Calculate the Van 't Hoff factor and the dissociation. See, for Van 't Hoff factor, it is observed divided by calculator. That is I, we studied right here. Here, Van 't Hoff factor. And if we see that it is 0.6 into 1.06 divided by total, like you find out the moles here, and you will get as 0.106 mole is equal to n, and the substitute here you will get delta tf. If you find, you will get this value. You substitute this here and 0.205 here we have got, right? And now let's see, 0.0205 is given in observed, and if you take the diagram, CH3COH gives to H plus ions and CH3CO minus. I is equal to n of 1 plus x. 1 plus x is equal to 1.041, which we have got here, 1.041. And if you find out, the Ka will be CH3CO minus divided by total, and that will be, if you calculate this here, you will get as 1.86 into 10 raised to minus 5. Okay, now I hope you understood the whole chapter of solutions. If you have any doubts, please let me know in the comment box, and please make sure to like, share, comment and subscribe to my YouTube channel. And thank you for watching the full video. Stay tuned.